Welcome back to the course of Applied Elasticity. In today's lecture, we are going to start our discussion on a new topic which is called thermoelasticity. So, what do we mean by this thermoelasticity or thermoelastic deformation problems? So, thermoelasticity is the study in which we are concerned with the prediction of the stress distribution and deformation of the elastic continuum when the body or the elastic continuum is subjected to combined mechanical and thermal loading. So, if there is a body which is not only subjected to mechanical loading, this is subjected to combined mechanical and thermal loading, then solution of that problem falls under the category of thermoelasticity, falls under the domain of thermoelasticity. So, using the thermoelastic problem solution approach, we would be getting the stress distribution and displacement deformation patterns of the elastic continuum whenever it is subjected to the combined mechanical as well as thermal loading. Now, coming to various engineering applications where these thermoelastic problems are required to be solved. So, if you consider the different components of the thermal power plants, those are subjected to the very high value of temperature. Along with that, there will be mechanical loads which may be coming due to the fluid pressure within the pipes or the other components of the thermal power plant, so called heat exchangers, reheaters, superheaters, all these will be subjected to some fluid pressure, and then they will also be subjected to very large temperatures. So, it will be a combination of the thermal and the mechanical loads. Similarly, the turbine blades, gas turbine blades or different parts of the engine, IC engine, they are subjected to mechanical as well as thermal shocks. So, it is also another example of the combined mechanical and thermal loading. During welding and coating also the thermomechanical loads are subjected. Similarly, if you consider the aircraft structures, they are subjected to cyclic aerodynamic heating. So, temperature is going up and down in a cyclic manner, which is giving the cyclic heating, cyclic thermal loading, and along with that the mechanical loads are also acting on the aircraft structure due to the high pressure. So, hence all these are various applications, various real life engineering applications where we can see the bodies or the elastic continuums which being subjected to mechanical as well as thermal loadings. Now, the formulation which we had discussed till now, all such elastic problems were only considering the application of mechanical load. Various mechanical loads were there. It may be normal point force, concentrated force, it may be distributed force, it may be moment, it may be twisting moment, anything, but all those are only or purely mechanical loads. Now, if thermal loads are also acting on the problem, then there should be some extra amount of stress or strains generated due to the thermal loading as well. Now, for thermoelasticity solution approach, we are going to consider effect of both mechanical loading on the continuum or body and thermal loading on the elastic body and continuum. So, first moving to the constitutive equations of thermoelasticity. So, for the mechanical loading, mechanical stress and generated mechanical strain, they were related with the help of constitutive equations. So, we had obtained the constitutive relations for various types of material, and for the linear elastic isotropic solid, we have seen that the stresses and strain components can be related with the help of only two material constants, but that is for a purely mechanical loading problem. If we add thermal loading to the system along with mechanical strains, thermal strains would be generated, and thus that constitutive equation is required to be modified. So, the first task for studying thermoelasticity is to understand the relation between the state of stress and state of strain for a body subjected to both mechanical and thermal loading. So, starting with the concept of thermal strain. So, this is the strain produced within the body due to the applied temperature variation or due to the thermal loading. So, due to thermal loading there will be a variation of temperature, change in temperature within the body, which will give rise to the thermal strain. So, let us write epsilon xx prime, epsilon yy prime and epsilon zz prime as the normal thermal strain component. So, this is the strain component along three normal directions which is produced only due to thermal loading. No, we are not considering mechanical loading here, and all of them are equals to alpha times T, whereas the shear components of the thermal loading for all three case directions epsilon prime xy, epsilon prime xz, epsilon prime yz would be 0. Now, alpha is the coefficient of thermal expansion of the material and T is the change in temperature due to the application of the thermal loading. So, with the help of this material constant alpha, this is another material constant. So, apart from the Poisson ratio nu and Young's modulus E and modulus of rigidity G, this coefficient of thermal expansion would be the another material constant which would be coming in the constitutive equation for the case of thermomechanical problems, and T is the change in temperature which would be multiplied with alpha to predict the normal thermal strains, but no thermal shear strains can be generated due to increase in the temperature T. Now, these strain equations can be combinedly written in the initial notation as epsilon prime ij equals to alpha T delta ij, where this delta ij is the Kronecker delta. So, if I equals to j, delta ij is 1, if I not equals to j, delta ij is 0. So, for all shear stress cases delta ij would be 0 and thus epsilon prime ij is 0 for I not equals to j. For I equals to j case delta ij being 1, all three normal strains, normal thermal strain components would be equals to alpha 3. So, here I and j can take the values of x, y and z, and this epsilon ij prime refers to the thermal strain component generated within the body due to thermal loading. Now, the total strain within the body will be coming due to contribution of both mechanical strain and the thermal strain. So, total strain is summation of mechanical strain generated due to mechanical loading and thermal strain generated due to thermal loading. Now, expressions of the mechanical strain is well known to us. So, epsilon xx written on the left hand side, this is the total strain, total normal strain generated along the x axis, which is normal strain due to mechanical component of the loading, which is the first term. This is the mechanical normal strain along x axis and this is the thermal normal strain along x axis, which is nothing but alpha T. And in terms of the mechanical stresses, we can write epsilon xx mechanical as 1 by E times sigma xx minus nu sigma yy minus nu sigma zz. So, total epsilon xx will be summation of the first term, which is mechanical component of the normal strain plus alpha T, which is the thermal normal strain. In a same fashion, all other normal strain components epsilon yy and epsilon zz can be written as shown here. So, whatever mechanical strains were there for the normal part, we are just adding one alpha T with all the normal strains, whereas the shear strain components epsilon xy, epsilon yz, epsilon xz, they remains unaltered because the thermal shear strains are 0. So, total shear strain is equals to only mechanical shear strain. There is no contribution coming on the shear strain component because of the thermal loading. So, these are the 6 equations which relates the stress components with the strain components and the temperature variation T, and alpha is another property coefficient of thermal expansion coming in these constitutive equations. Now, we will try to write this constitutive equation in a concise form using the initial notation. So, we know that the volumetric strain small e or epsilon kk, that is stress of the strain tensor epsilon, is written as epsilon xx plus epsilon yy plus epsilon zz. Now, all these epsilon xx, yy and zz, three normal strain components for the thermomechanical problem we had obtained like this just in the previous slide. So, substituting these total normal strain component epsilon xx, epsilon yy, epsilon zz in the expression of the volumetric strain or dilation epsilon kk. This dilation can be written like this: 1 by E times 1 minus 2 nu times sigma xx plus sigma yy plus sigma zz plus 3 alpha t. So, for only mechanical problem, this first term was there. Due to this thermal part, this each of the epsilon xx is contributing 1 alpha t term. So, in the volumetric strain there would be 3 alpha t term, which is coming due to 3 different normal thermal strain components. Now, rewriting E from this, we can write E as sigma xx plus sigma yy plus sigma zz by 3 k plus 3 alpha t. Now, what is k? K is the bulk modulus. We had discussed about all these different properties of the linear elastic homogeneous isotropic solids: E, K, nu, G, lambda and mu. Lambda and mu are Lamé constants. They can be related with the commonly known constants Young's modulus E, shear modulus or modulus of rigidity G, Poisson's ratio nu and bulk modulus K. Those relations we had earlier derived. So, one such equation we are using here, which is k equals to E divided by 3 times 1 minus 2 nu. So, in the first term, this 1 minus 2 nu by E I am writing as 3 k. Thus, the volumetric strain or dilation epsilon kk or small e would be sigma xx plus sigma yy plus sigma zz by 3 times bulk modulus plus 3 alpha t. Now, from this we can write summation of sigma yy and sigma zz. So, our objective is to replace sigma xx and sigma yy in the first strain expression epsilon xx in terms of sigma xx. So, this part of sigma yy and zz I want to write in terms of sigma xx, so that on the right hand side of epsilon xx only one normal stress corresponding to epsilon xx is present, that is sigma xx. So, from this we are keeping these parts sigma xx plus yy on one side and sending all rest to right hand side. So, sigma yy plus sigma zz would be 3 k times E minus 3 alpha t minus sigma xx, and now replacing these expression of sigma yy plus sigma zz here in epsilon xx equation right hand side. The epsilon xx can be written like this: 1 by E times within bracket sigma xx minus 3 nu k times small e, that is dilation, minus 3 alpha t plus nu sigma xx, and then outside the bracket the thermal strain component alpha t. Now, if I expand this in terms of sigma xx, so sigma xx, keeping this sigma xx on one side and sending everything on another side, the dilation, the normal strain epsilon xx and the thermal part alpha t, all those are sent on right hand side. So, sigma xx expression in that case would be looking like this. We are having three terms. Sigma xx is dependent on dilation or volumetric strain small e, it is dependent on corresponding normal strain epsilon xx, it is also dependent on the thermal strain alpha t, and all these terms are having a coefficient 3 nu k by 1 plus nu, then E by 1 plus nu and minus E plus 3 nu k divided by 1 plus nu respectively. Now, all these are material constants, they are related, these constants are directly related with different material constants. Now, from this E, nu, k, all these material constant we will try to write in terms of the Lamé constant lambda and mu. So, if you recall the relation between these commonly available material constant and the Lamé constant, all those relations are presented here, which we had derived once while discussing about the constitutive equation for the isotropic solids. Now, using these equations of E Young's modulus E, then shear modulus G or mu, then Poisson ratio nu and bulk modulus K, we can write each of them in terms of lambda and mu, that is two quantities which are known as the Lamé constant. With that, these first term 3 nu k divided by 1 plus nu can be written as lambda, and this last coefficient E plus 9 nu k divided by 1 plus nu, E plus 9 nu k divided by 1 plus nu can be written as 3 lambda plus 2 mu, and this central term, the coefficient of the middle term E divided by 1 plus nu. Using this equation, this is nothing but 2 times mu, and hence sigma xx becomes lambda times E or lambda times epsilon kk plus 2 mu epsilon xx minus 3 lambda plus 2 mu times alpha t. So, this is the relation between the normal stress sigma xx and shear stress epsilon xx, sorry, the normal stress sigma xx and the corresponding normal strain epsilon xx along the x direction for a thermomechanical problem. Now, if you try to recall this equation, corresponding equation for a purely mechanical problem, this term was not there. This is the extra term coming. For a mechanical problem, we had sigma xx to be lambda epsilon kk plus 2 mu epsilon xx, that is all. Now, here this additional term minus 3 lambda plus 2 mu times alpha t is coming due to the thermal strain. Now, similarly, you can write sigma yy, sigma zz, other two normal stress components in a similar fashion like this, and as there is no thermal shear strain generated, the constitutive equation for the shear stress and shear strain components remain same. So, tau xy, tau yz, tau xz is equals to 2 mu times epsilon xy, 2 mu times epsilon yz and 2 mu times epsilon xz respectively. So, these are the 6 constitutive equations for any thermomechanical problem, which can be combined to a single equation written in indicial notation form like this. So, sigma ij is equals to lambda epsilon kk delta ij. This term, due to presence of this Kronecker delta ij, would be non-zero only if I equals to j. So, that term is resulting this lambda epsilon kk only for the normal stresses. For the shear stress components I not equals to j, so this term would vanish. Second term is present for all 6 cases, which is 2 mu epsilon ij, and last term minus 3 lambda plus 2 mu alpha t delta ij. This is also once again present only for the normal terms. So, that is why delta ij or Kronecker delta is added here in the last term. So, last term is also present only for I equals to j or for the normal stress normal strain relations. Now, rewriting k as 3 lambda plus 2 mu by 3, that is relation between bulk modulus and Lamé constant, we can rewrite this equation sigma ij equals to lambda delta ij epsilon kk plus 2 mu epsilon ij minus 3 times bulk modulus k alpha t delta ij. This is the constitutive equation which is known as Duhamel-Newman thermoelastic constitutive equation, which is required to be used for writing or relating the total stress with the total thermoelastic strain containing both mechanical and thermal components. So, this last term is extra, which gives us the effect of the change in temperature T, which includes two material constant, one is bulk modulus K, another is the coefficient of thermal expansion of the material alpha, coefficient of linear thermal expansion. Now, moving forward to the formulation of the thermoelasticity problem in plane or 2D thermoelasticity problem, which may be either of plane stress type or may be of plane strain type. So, coming to the assumptions of the thermoelastic plane stress problem, first we are considering one thermoelastic problem with plane stress approximation, for which all the out of plane stresses sigma zz, out of plane normal stress, tau xz and tau yz, the out of plane shear stresses are neglected for this plane stress assumption, which is valid for the geometry, with geometry of the body being thin in the z direction. For such cases, these three out of plane stress components being 0, the equilibrium equations after neglecting the body forces would be like this: del sigma xx del x plus del tau xy del y equals to 0, and del tau xy del x plus del sigma yy del y equals to 0. These are the only two equilibrium equations available for the thermoelastic plane stress problem, where these two equations can be automatically satisfied by choosing the stress components, the in plane stress components, in terms of a stress function known as Airy's stress function phi as sigma xx is equals to del 2 phi del y2, sigma yy is del 2 phi del x2, and tau xy is minus del 2 phi del x del y. So, if we choose the stress components like this, we know that then both the equilibrium equations would be automatically satisfied. Now, we will try to write the strain components for this thermoelastic plane stress problem. Now, strain components are having this additional thermal strain term present. Considering the normal strain in the x direction epsilon xx, that is equals to 1 by E times sigma xx minus nu sigma yy. Note that as sigma zz equals to 0, we are not having any term minus nu sigma zz here in the epsilon xx. Sigma zz is already 0 because of the plane stress nature of the problem. Now, substituting sigma xx as del 2 phi del y2 and sigma yy as del 2 phi del x2, epsilon xx would be like this: 1 by E times del 2 phi del y2 minus nu times del 2 phi del x2 plus alpha t. So, first term, this one is the mechanical normal stress in strain in x direction, alpha t is the thermal normal strain in x direction. Similarly, another normal strain in y direction epsilon yy can be written as 1 by E times del 2 phi del x2 minus nu times del 2 phi del y2 plus alpha t. And the third one epsilon zz, the axial normal strain can be written as minus nu by E sigma xx plus sigma yy plus alpha t, and replacing sigma xx and sigma yy as del 2 phi del y2 and del 2 phi del x2 respectively, these terms would give us Laplacian of phi. So, epsilon zz would be minus nu by E Laplacian of phi plus alpha t. So, these are the three normal strain components for a thermoelastic plane stress problem, and the only non-zero shear strain component epsilon xy can be written in terms of corresponding shear stress component tau xy as 1 plus nu by E times tau xy, replacing tau xy as minus del 2 phi del x del y. We can write this as epsilon xy is minus 1 plus nu by E del 2 phi del x del y, and other two shear strain components out of plane shear strains epsilon xz, epsilon yz to be 0, as we have tau xz and tau yz to be 0. So, these are the 6 thermal strain component, thermoelastic plane stress problem strain components. Now, using these, we must satisfy, using these non-zero in plane strains, we must satisfy the strain compatibility equation for this thermoelastic plane stress problem, and then only the unique displacement field can be ensured. So, for the 2D problem, only compatibility equation which is left out to be satisfied is this: del 2 epsilon xx del y2 plus del 2 epsilon yy del x2 is equals to 2 times del 2 epsilon xy del x del y. So, here this epsilon xx, epsilon yy and epsilon xy, are replaced in terms of these equations. So, replacing these here, if I simplify this, so all the terms on the left hand side, the first set of terms are the terms which are having Young's modulus 1 by E as common factor, then the alpha dependent terms are written here, and the right hand side are the terms coming from the epsilon x y. So, if I rewrite this using the Laplacian and biharmonic operator, this equation would be biharmonic of phi plus E alpha Laplacian of t equals to 0, or biharmonic of phi would be minus E alpha Laplacian of t. So, this is the governing equation for choosing the stress function phi for a thermoelastic plane stress problem. If you recall, for a purely mechanical 2D plane stress problem, we are just supposed to satisfy our eddy stress function should just satisfy del 4 phi equals to 0. Now, from this equation, if we want to go back to the purely mechanical problem, then we must force T equals to 0. So, if you say there is no change in temperature with T equals to 0, this governing equation for thermoelastic plane stress problem would be reduced to the governing equation of purely mechanical plane stress problem, where phi has to be just biharmonic. Here the biharmonic operator acting over phi, del 4 phi should be equals to minus E alpha Laplacian of t. So, for a given temperature distribution T, for a given change in temperature field T, we need to find Laplacian of t, then minus E alpha Laplacian of t should be equals to biharmonic of phi. Accordingly, the stress function should be chosen for the thermoelastic plane stress problem. Now, moving forward to the thermoelastic plane strain problem in a similar manner, where the body is supposed to be or assumed to be very large along z direction, so that the out of plane strain components epsilon zz, epsilon xz, epsilon yz can be neglected. Epsilon zz being 0, we can write the total mechanical plus thermal component of epsilon zz is 0. So, 1 by E sigma zz minus nu sigma xx minus nu sigma yy plus alpha t is equals to 0. So, the first term is the normal strain in z direction for mechanical, alpha t is normal strain in z direction for thermal loading. Now, from this we can write sigma zz as nu times sigma xx plus sigma yy minus E alpha t. So, sigma zz is non-zero for the plane strain problem, and that is related with the other stress, other normal stresses and the temperature field using these particular equations. Now, moving forward to the equilibrium equation, they are same as the case of plane stress problem. So, equilibrium equation for any 2D problem, plane stress or plane strain are same, and thus we can have a same type of choice of stress components in terms of eddy stress function phi, as sigma xx is del 2 phi del y2, sigma yy is del 2 phi del x2, tau xy is minus del 2 phi del x del y. So, in terms of these chosen stress components, we can write the strain component like this. So, the first one, normal strain along x direction for a plane strain thermoelastic problem, epsilon xx would be 1 by E sigma xx minus nu sigma yy minus nu sigma zz plus alpha t, where replacing sigma xx with del 2 phi del y2, sigma yy with del 2 phi del x2 and sigma zz using this equation, in which once again this sigma xx and sigma yy is required to be replaced in terms of phi. If I do so and simplify, the final expression of epsilon xx, the normal strain along x direction would be 1 by E times del 2 phi del y2 minus nu del 2 phi del x2 minus nu square Laplacian of phi. This is mechanical part, plus 1 plus nu times alpha t. This is the thermal part. So, this gives us the total expression for normal strain along x direction for the thermoelastic plane strain problem. Similarly, we can get the other strain components epsilon yy, another normal strain like this, and the shear strain epsilon xy. In plane shear strain epsilon xy would be minus 1 plus nu by E del 2 phi del x del y, which is same for both plane stress and plane strain problems. And rest free out of plane normal and shear strains epsilon zz, epsilon xz, epsilon yz are 0 for the plane strain assumption. So, we got the strain fields, written them in terms of the phi, the eddy stress function. Now, moving forward to the strain compatibility equation, which is required to be satisfied for ensuring the unique displacement field. So, the only strain compatibility left out to be satisfied for the thermoelastic plane strain problem is del 2 epsilon xx del y2 plus del 2 epsilon yy del x2 plus equals to 2 times del 2 epsilon xy divided by del x del y, same as the plane stress compatibility equation for the 2D problems. Now, substituting epsilon xx, epsilon yy and epsilon xy using these equations in terms of phi and simplifying this further, the strain compatibility equation gives us this 1 minus nu square biharmonic of phi plus 1 plus nu times E alpha Laplacian of t equals to 0. Now, cancelling this 1 plus nu factor from this 1 minus nu square, we would be left with only one term, which is Laplacian of phi plus E alpha biharmonic of phi plus E alpha Laplacian of t divided by 1 minus nu equals to 0. And if you are taking this term on the other side, in that case the biharmonic of phi would be equals to minus E alpha Laplacian of t divided by 1 minus nu. So, this is the governing equation for choosing the stress function phi for the thermoelastic plane strain problems. Here also, if you substitute t to be 0, it will be reduced to the corresponding mechanical plane strain problem with del 4 phi equals to 0. So, phi should be biharmonic, but here it is biharmonic operator del 4 phi equals to minus E alpha Laplacian of t by 1 minus nu if we are considering thermoelastic plane strain problem. So, both for thermoelastic plane strain and thermoelastic plane stress, we are having one governing differential equation based on which the choice of phi, choice of stress function is dictated. So, in this lecture we had discussed about the introduction to the thermoelastic problems. We had derived the thermoelastic constitutive relation for the isotropic solids, and finally discussed about the formulation for thermoelastic plane stress and thermoelastic plane strain problems. Thank you.